Hi everyone, this is Kiranmai from H&S department. Today in this session, we are going to discuss about Hall effect. Under this topic, we are going to discuss about statement, experiment regarding Hall effect, applications for the Hall effect, and some numericals depending on Hall effect. First of all, what is Hall effect? What states that? So this Hall effect deals with the uh, application of two different fields on a current carrying conductor. What happens when a magnetic field is applied on a current carrying conductor? See, when suppose a material is carrying an electric current is placed in a magnetic field, then what happens? Then electric field is produced inside the material in a direction which is at right angles to the both current and magnetic field. This effect was first discovered by Edwin H. Hall in the year of 1879, and the phenomena is known as Hall effect, and generated voltage is called as Hall voltage. Now, actually, what happens with the semiconductor material? For suppose, let us consider one semiconductor material which is carrying a current I from the red phase to the blue phase. So, if current is from left side to right side, then flow of electrons will be from right side to left side. So, when this semiconductor material, which is carrying a current IH, is placed in a external magnetic field, which is whose direction is from front face to back face, which is perpendicular to the flow of current, then what happens? Due to the force, magnetic field force, the electrons which are moving from right side to left side, due to that force, they will get accumulated on one of the face of the semiconductor material. Due to the negative force on one of the face, the opposite face will be positively charged. Hence, a voltage will be developed between those two faces called as Hall voltage, which is perpendicular to both the flow of current and the flow of magnetic field. This is called Hall effect, and the produced voltage is called as Hall voltage. To find out how much Hall voltage is produced in the circuit, let us consider a semiconductor, N-type semiconductor material. Let V be the velocity of the electrons flowing from right to left, just opposite to the conventional flow of current. So the magnetic field is applied perpendicular to the flow of current. See, electrons are moving from right to left, flow of current is from left to right, and magnetic field is applied from front to back side of the semiconductor cube. So what this direction of the magnetic field is just perpendicular to the flow of current. Then electron experience a force, magnetic force, equal to BQV, where Q is charge of electron. So BEV is the force experienced by an electron when it is placed in an external magnetic field. So thus electrons deflected, causing a negative charge to accumulate on one face, and the potential difference is therefore established between the phase, gives rise to electric force QE. Force due to electrical charges is F is equal to QE. So since we are talking about electrons, in place of Q we are going to take charge of electron. So F is equal to EH, where E is small e is charge of electron, EH is produced electric field. So at equilibrium position, force due to electric field and force due to magnetic field balance each other. Therefore, EEH is equal to BEV. So on both sides, you can cancel the charge of electron, left off with Hall field. EH, Hall field, EH is equal to applied magnetic field in and velocity of electron. Since we know that J is the charge current density, which is defined as NEV, product of charge of carriers, number of carriers into charge of carrier into velocity of that carrier. Then from this rearrangement, you can write velocity V is equal to J by NE. So Hall field is equal to B into J by NE, where 1 by NE is called as Hall coefficient. Therefore, EH Hall field is equal to BJ into RH, where applied field, current density, and Hall coefficient. RH is called as Hall coefficient. Since the quantities are measurable, applied field, as we know the applied field, how much current density will be produced, and Hall coefficient, we can easily calculate the current density, carrier density, and can be founded out. So coming to the applications of Hall effect, first the main application of Hall effect is to determine the type of the semiconductor. So depending upon the Hall coefficient value, we can either we can either determine the material is an N type or P type. So if the Hall coefficient value is negative, then the given semiconductor will be an N type material. If the Hall coefficient value is positive, then the given material is an P type material. This was the first application of Hall effect for the determination of type of a semiconductor. Second one, determination of Hall coefficient. How to find out Hall coefficient value? For that, let B with the width of the sample across which Hall voltage is measured. See, in the dimension in which you are supposed to measure the Hall voltage, in that dimension, let B with the width. Then depending upon that, VH is equal to EH into the relation between potential and the electric field. So, and we know that Hall field is given by Bj into RH. So in place of EH, just reproduce this one. So VH is equal to RH BBJ. Now from this, if you rearrange the terms, you'll get RH is equal to VH by BBJ, where J is current density. Current density is nothing but a flow of current by current per unit area. Current per unit area, I by AT, where area we can write it as width into thickness, B into T, I by B into T. So VH is equal to RH BB into I by BT, where BB, if you cancel out, you are left with VH is equal to RH B I by T. Just rearranging the terms, you will get Hall coefficient value as RH is equal to VHT by BI. B value, we know that as we applied the magnetic field, I flow of current, how much current is flowing through the circuit. T is the thickness of the semiconductor sample what you had taken. VH is the potential that has been produced due to application of magnetic field on a current carrying conductor. By knowing all these terms, if you substitute it, we can get the Hall coefficient for that particular material. Next. Third application for the Hall effect is determination of mobility. To determine the mobility, let us consider the conductivity of the material. Sigma is equal to Ne mu, where mu is called mobility. Now rearranging the terms will give you mu E is equal to sigma by Ne. 1 by Ne is nothing but RH, so mu A is equal to RH sigma n, mobility of electrons. Similarly, mobility of protons, mobility of holes can be given as RH into sigma P. Next, determination of carrier concentration. As we know that RH is equal to 1 by Ne, just rearranging the terms will give you N is equal to 1 by RH into E. Just knowing the Hall coefficient, we can calculate the carrier concentration. Then coming to the magnetic flux density, using the Hall coefficient formula, just rearranging the terms, you will get B is equal to VHT by RHI, where VH, by knowing the Hall coefficient, magnetic flux density can be measured by measuring the Hall voltage. Coming to the numericals dependent on this Hall voltage, Hall coefficient, mobility and all. Let us see one of the problem where they have given the dimensions of the silicon plate, which is carrying a current of 10 power minus 2 amperes and the magnetic field of 0.5 Weber per meter square is applied on it. Then they were asking you to find out how much Hall voltage will be produced or developed if the Hall coefficient value is the 3.6 into 10 power minus 4 meter cube per coulomb. Just writing down the terms given, they had given you the Hall coefficient, current flowing through, applied magnetic field and the thickness of the material. Substituting them in the Hall voltage formula, VH is equal to RH BI by T, you just can can calculate Hall voltage. Next, another type of problem where they had given the dimensions of the material and the flow, how much flow of current is there for a magnetic flux density of 0.5. They had given a Hall voltage also, that is 37 microvolts. They were asking you to find out Hall coefficient. What is the formula? RH is equal to VHT by BI. VH, Hall voltage, they had given 37 microvolts, that is 37 into 10 power minus 6 volts. Thickness T is given as 1 mm, so 1 mm can be written as 1 into 10 power minus 3 meters. And current is 20 milliamps, so 20 into 10 power minus 3 amperes. And the magnetic field is 0.5 Weber per meter square. Now substituting them together in this formula, you'll get another value 3.7 into 10 power minus 6 meter cube per coulomb. Another problem where they had given you the Hall coefficient and resistivity value, and they were asking you to measure mobility. RH and rho value they had given you, they were asking you to find out mu. Generally, mu is equal to sigma n into RH, where sigma is the conductivity. So, conductivity in terms of resistivity can be written as reciprocal. So, RH by rho, where rho is the resistivity. So, substituting those two values in the formula, you'll get mobility of the particles with a resistivity of 8.93 into 10 power minus 3 ohm meter. Thank you.